Another famous machine-assisted proof, well, actually initially human proof, but eventually computer verified, was the proof of the Kepler conjecture. So the Kepler conjecture is a statement about how efficiently you can pack unit spheres in the plane. And so there's a natural way to stack unit spheres, and it's the way that you see oranges stacked in the grocery store. It's called the hexagonal closed packing. And there's also a dual packing with the same density called the cubic closed packing. And they have a certain density, pi over 3√2. And this was conjectured to be the densest packing. So this is an annoyingly hard statement to prove. It's an optimization problem in infinitely many variables. So there's this each sphere has a different location, and there's an infinite number of spheres. So you're trying to prove an inequality involving an infinite number of variables involving solving an infinite number of constraints. So it doesn't immediately lend itself to computer verification. But even in the 50s, it was realized that possibly this could be done by some sort of brute force computation. And so Toth proposed the following paradigm. So every time you're sphere packing, it comes with what's called a Voronoi decomposition. So every sphere comes with a Voronoi cell, which is this polytope of all the points that are closer to the center of that sphere than to all the other spheres. And this partitions space into all these little polyhedra, these Voronoi cells. There are various relationships between the volumes of these different cells. There's only so many spheres that you can pack next to one reference sphere, and this creates all these kind of constraints. And so the hope was that if you could gather enough inequalities between adjacent Voronoi cells, the volumes of adjacent Voronoi cells, maybe every such system of inequalities in principle gives you an upper bound on the density of a sphere packing. And in principle, if you get enough of these inequalities, maybe you could actually get the optimal bound of 3√2. So people tried this approach for many, many years, and including some false attempts. But they were not able to actually make this approach work. But Thomas Hales, and then later with a collaborator, was able to adapt this approach to make it work in a series of papers from 94, 98. But they had to modify the strategy quite a lot. So instead of using the Voronoi decomposition, there was a more complicated decomposition that was used. And instead of using volume, they had to define this new score function attached to each polyhedron. But basically, the strategy was the same. And he was able to prove lots and lots of linear inequalities between the scores of adjacent polyhedra. And then just using linear programming, was able to then get a bound. And with the right choice of score and the right choice of partition, it was the optimal bound. It's a very flexible method because you have lots of ways you can do the partition and lots of ways that you can do the score. But it was actually, the problem is that it was too flexible. So here's a quote from Hales. It says that Samuel Ferguson, who was Hales' collaborator, and I realized every time we encountered difficulties solving the minimization problem, we could adjust the scoring function to scale the difficulty. The function became more complicated, but with each change, we could cut months or years from our work. This incessant fiddling was unpopular with my colleagues. Every time I presented my work in progress at a conference, I was minimizing a different function. Even worse, the function was mildly incompatible with what it did in earlier papers, and this required going back and patching the earlier papers. So the proof was a mess, basically. They did eventually finish it in 98, and they were able to derive the Kepler conjecture from a linear programming computation, from a very complicated optimization program. Initially, it was done by hand, but with the increased complexity, there was no choice but to make it more and more computer assisted. So when the proof was announced, the proof had, it was a combination of 250 pages of notes and lots and lots of gigabytes of programs and data. And it was famously hard to referee. It took 4 years for annals to referee the paper with a panel of 12 referees. And even then, the panel were only 99% certain of the correctness of the proof, and they couldn't certify the corrections, the calculations. Because, I mean, in principle, like, it was all doable, but, like, the referees have to sort of implement all these different computer calculations themselves. But it was eventually accepted. But clearly, there was this big asterisk. There was a lot of controversy about whether this was really a valid proof. And so this was one of the first really high-profile uses of formal proof assistance, because this was a result in which there was serious doubt about the correctness. So they created, so Hales in 2003 initiated a project to write down this massive proof in a completely formalized way so that a standard proof assistant could verify it. He estimated it would take 20 years to make this work. And so with he gathered 21 collaborators. It actually only took 11 years. Yeah, eventually what they did was that they first created a blueprint, so a human-readable version of the proof, breaking things up into very, very small steps, and then they formalized each step bit by bit. And it was finally done. And then there was they published a paper about the formalization, and that only appeared in 2017. So this was sort of the state of the art of formalization, as of say 20 years ago. Like it was possible to formalize big, complicated results, but it took enormous amounts of effort. Not something which you would do routinely. There was a more recent effort in a similar spirit by Peter Schulze. He called it the liquid tensor experiment. So Schulze introduced this theory of condensed mathematics, which is, all right, this is really far from my own area of expertise, but basically there are certain problems with, certain types of mathematics, you want to work in various categories, like categories of topological Abelian groups and topological vector spaces. And there's a problem that they're not Abelian categories, that they don't have a good notion of kernel and co-kernel, and things don't work out properly. So he proposed replacing all of these standard categories with a more fancy version called a condensed category, which has better category theoretic properties. And so the hope then is that you can use a lot more high-powered algebra to attack, to handle things with topological structure or analytical structure, like function spaces, for example, Banach spaces. But in order for the theory to work, there's a certain vanishing theorem which I've written there, but I cannot explain to you. Okay, so there's a certain category, condensed Abelian groups, and there's a certain X group involving P Banach spaces that has to vanish. This vanishing theorem is needed in order for all of the rest of the theory to actually be useful. If you want to apply it to functional analysis in particular. And so Schulze wrote a blog post about this. He said, I spent much of 2019 obsessed with the proof of this theorem, almost getting crazy over it. In the end, we were able to get an argument pinned down on paper, but I think no one else has ever dared to look at the details of this, and I still have some lingering doubts. With this hope, with this theorem, the hope that the condensed formulas can be fruitfully applied to functional analysis stands or falls. Being 99% sure is not enough because this theorem is of the most utmost fundamental importance. He says, I think this may be my most important theorem to date, which is a really big claim, actually. Better be sure it's correct. So this was another case where there was a great desire to formalize the proof. So he asked publicly on the internet for help to formalize this in a modern proof assistant language called Lean. And so, again, about 20 people, I think, joined this project to help out. So Lean is based on, it has this philosophy where it has this single huge library of mathematical theorems, like the fundamental theorem of calculus or the classification of finite Abelian groups. Like a lot of the basic theorems of mathematics are already formalized in this big library, and the idea is to just keep building on this library and adding to it with additional projects. But one of the problems that Schulze faced was that a lot of the basic tools that he needed, like homological algebra and sheaf theory and topos theory, weren't actually in the library yet. So actually part of what they had to do was actually set up the foundations of that theory and formalize it in the library first. But it basically was done in about 2 years. In 1 year, they formalized a key subtheorem, and then the whole thing was formalized about a year afterwards. It did have some, in addition to sort of making reassuring Peter that everything was correct, there was some other minor benefits. So first of all, there were actually a few minor errors in the proof that were discovered in the formalization progress, but they could all be fixed. Also, some small simplifications. There was one big simplification actually. So the original proof used something very complicated, which I also don't understand, called the Breen-Deligne resolution. But in the course of formalizing it, it was too hard to actually formalize this theory, but they found that there was a weaker version of this theory which was good enough to formalize this application. But this was actually a major discovery because this weaker theory could also potentially attack some other problems that the Green-to-Lean resolution is not well suited for. And now the math library is much, much better it has a lot of support for homological algebra and sheaf theory and lots of other things, which helped other formalization projects become easier. I got interested in this formalization a few months ago. Hang on. I should say, like with the Kepler experiment, so you don't just directly transfer a paper from the archive or something into Lean. What we found is that it really helps to create first an intermediate document, so halfway between a human readable proof and a formal proof, which we call a blueprint. So it looks like a human proof and is written in a version of LaTeX. But like each step in the proof is linked to a lemma in Lean. And so it's very tightly integrated. And it has a very nice, there's a very nice feature. It can create dependency graphs, which I'll show you an example later. You can see which parts of the proof have been formalized, which ones are not, and what depends on what. And it gives a lot of structure to the process of writing a paper, which right now we do by hand without sort of much assistance really. Yeah, Schulze said that the process of writing the blueprint really helped him understand the proof a lot better. And actually, people have been also going the other way. There's also software that takes formal proofs, which are written in something that looks like computer code, and turns them back into human readable proofs. Here is a prototype software. So there's this theorem in topology. Okay, I think it's if a function is continuous on a dense set and there's some extra properties, then it's continuous. It extends to a continuous function globally. And the proof was written first in Lean, but then it was automatically converted into a human proof, human readable proof. But again, where every step you can expand and contract. Like if there's a step you want to explain more, you can double click it and it will expand out, give all the justification. And you can click at any given point in the proof, and it will tell you what the hypotheses are currently, what you're trying to prove, and you can give a lot of structure. I think eventually textbooks. This is maybe a good format, say for undergraduate textbooks, to have proofs of, say, tricky theorems in analysis or something written in a way where, not in a static way, but where you can really, drill down all the way down to the basic axioms if you wanted to. Okay.